Welcome. I'm Tom Hinckley, Interim Director of the University of Washington School of Forest Resources. On behalf of the school and the College of the Environment, I welcome you to the 2010 Sustaining Our Northwest World lecture entitled Climate, Forests, and Future, A View from Treeline. Matching a desire to maintain a healthy social, economic, and environmental system in the Pacific Northwest with the pressures of climate change, development, and population growth challenges the members of the university and the citizens of the state of Washington. This lecture is just one example of the work going on at the School of Forest Resources to meet this challenge. The lecture is a companion to this school's Denman Forestry Issues series, also seen on UW-TV and the Research Channel. Both series contribute to the school's vision of a world-class knowledge and leadership for the stewardship of natural resources and environmental values for our own and future generations. I encourage you to visit our website at www.cfr.washington.edu to learn more about our research, education, and outreach program. We are pleased to present this lecture in partnership with the College of the Environment, of which our school is a founding unit, and the University of Washington Alumni Association. We are also grateful for the support of members of the school's Directors Club and the college's Dean's Club. Our lecture is presented by U.S. Forest Service research biologist and School of Forest Resources Professor Dave Peterson. Professor Peterson holds a PhD from the University of Illinois, and after almost a decade with the U.S. Forest Service's Pacific Southwest Research Station, moved in 1989 to a position with the National Park Service's Cooperative Park Studies Unit in Seattle and became a member of our faculty at that time. He established a research program on the effects of climate change on mountain ecosystems. He subsequently worked with the National Biological Survey and the U.S. Geological Survey before joining the Forest Service's Pacific Northwest Research Station in 2001. He currently directs the fire and environmental research applications teams there. His lecture is especially important in that the challenge of climate change, with its effects on forest health and forest fuels, will impact all of us in the Pacific Northwest. The challenge is so great that it can only be addressed through a collaborative process involving multiple disciplines and direct partnership with stakeholders. Professor Peterson presents a compelling case for this interdisciplinary approach, which, in essence, is the rationale for the creation of the University of Washington's new College of the Environment. Our Sustaining Our Northwest World lecture series, which became the inaugural lecture in the new College Dean's Lecture Series, is a cogent statement of the challenge and the promise of interdisciplinary collaboration. It is my pleasure to introduce U.S. Forest Service biologist and School of Forest Resources Professor Dave Peterson, who will speak on Climate, Forests, and Future, A View from Treeline.
I know it's traditional to say thank yous to the end of presentations, but I'd like to start out with my thank yous tonight, if you don't mind. First of all, I'd like to thank my wife, Linda, and my daughter, Christina, for their love and support and for tolerating my 60-hour work weeks for so many years. I'd also like to thank my parents, Vic and Lydia Peterson, who are no longer with us, but provided me with the opportunity and background to do whatever I wanted to do. As children who grew up during the Great Depression, neither one of them even had the chance to go to high school, but they did allow my brother and me to have opportunities to excel. I'd like to also thank my brother, Jerry Peterson. He taught me how to read. He got me interested in science, and he taught me how to hit the outside pitch to the opposite field, which had both practical and metaphorical value in my life. I'd like to thank my good friend and colleague, Dr. Don McKenzie, with whom I've worked now for over 15 years. He has always inspired me with his scientific skills and expertise, and he has really contributed a lot to what I'm going to say tonight. I'd like to thank all of my colleagues at the U.S. Forest Service and at the School of Forest Resources. It's been an amazing partnership, and most of what I've learned in the last 20 years or so has been due to their influence. And finally, I'd like to thank all the graduate students who've come through our program in the last 20 years. I will be presenting some of that research here tonight. And any accomplishments I might have done over the last 20, 30 years is really due to the influence of all the people that I just mentioned. So I've just pulled all that stuff together. Well, Al Gore couldn't make it tonight. And unfortunately, I could not afford his PowerPoint technology staff. So you're stuck with me and my minimal skills, and I'll try to do my best to convey a few things about arguably the most important scientific issue of our times, which is climate change. So this is kind of a strange way to start out a scientific presentation, showing you a picture of a light bulb. This is a kind of a typical Christmas tree light bulb. It says 1.6 watts, and 1.6 watts per meter squared is the radiative heat load at the Earth's surface due to human-caused climate change, which has accelerated over the last 150 years or so. So if we could take all these little light bulbs and array them across the surface of the Earth, we'd have about 500 trillion of them. So if you can, this is kind of a different perspective on the 1,000 points of light idea. So 1.6 watts doesn't sound like a lot, but if you get 500 trillion of these light bulbs over a long enough time, it clearly is now having some effects on the temperature at the Earth's surface and in the oceans. So I do this to just give you a little perspective on what climate warming really means. I also want to just take a little time to set the context for climate change. And so I have some graphs here with a little bit of data. They're not all that complex. I'll try to get us through this, and then we'll go to some pretty pictures. This is what I call one of the IPCC spaghetti graphs. And it's basically a graph of carbon dioxide emissions over time. And all the different noodles there in the pasta are essentially different scenarios, different economic and policy scenarios as defined by the Intergovernmental Panel on Climate Change. So the ones down at the bottom, the greens and blues, are basically scenarios for the future in which we work together, we reduce emissions, and we collaborate amongst nations of the world to address climate change. The lines up towards the top, the reds and the oranges, marked by A, the letter A, are pretty much business as usual, continuing to accelerate emissions over time. Now you see that little red box, so let's zero in on that red box, which is just the last 20 years or so. Again, you see all these different colored lines, and you see them compared to the actual emissions in the dark lines. Now, what I'm going to show you next is the actual trajectory of emissions. That upper red solid line is the highest end scenario that was used by the IPCC, and we are considerably above that. So that's not a good thing. We are beyond the point, we're beyond this envelope that has been investigated so far. Let's continue with this a little bit. This is a simulation of a couple of these different future scenarios projecting global surface warming over time for the next 300 years. And so again, we see the blue, which is a low-end emission scenario. We see the green, which is a mid-range emission scenario. And we see the red, and we see again that little dotted red line is going up pretty fast. So I'm not a gloom and doom kind of guy, but this is a great source of concern, and this is one of the reasons why there's such urgency to addressing climate change as a societal issue. Zeroing in on the Pacific Northwest, these are the latest modeling results that have been generated by the Climate Impacts Group, which is part of the College of the Environment. And let me try to walk you through this one a little bit. The yellowish envelope that you see there is a lower emission scenario. The reddish envelope is a higher emission scenario. The place where they intersect, you can see there, and we have kind of a best fit line, that little solid red line. Bottom line is by the year 2100, we expect it to be about 7 degrees warmer in our region. So that sounds like a lot, maybe, or maybe it doesn't. But let's try to put that in perspective so you know what this means to you personally. So, right here in Seattle, our current summertime average temperature is about 65 degrees. So that's, including both daytime, nighttime temperatures, 65. Average wintertime temperature is about 41 degrees. So we expect in about 90 years that summer temperature will go up 7 degrees to 72. Winter temperature will go up about 7 degrees to 48. Well, again, that doesn't mean that much. So let's compare it to cities in the United States that currently have those temperatures. So future summer temperature looks more like what these cities are now: Asheville, North Carolina, Chicago, Denver, Pittsburgh, and Reno. To me, that doesn't sound too good. That sounds like a pretty unpleasant future in some respects. Let's look at the winter temperatures. Charleston, South Carolina, Las Vegas, Montgomery, Sacramento, and Savannah. And I can see some of you smiling about that. So that might not be too bad to have a warmer winter in Seattle. Maybe kind of like this winter that we've been having due to El Nino. But this puts things in perspective, gives it a little bit of a human touch. I know a lot of people try to express to their friends, what will it be like in the future? The numbers don't mean much, but if you tell them about these cities, it might have a little bit more meaning. When I moved to Seattle to take a job with the Park Service in 1989, I was tasked by my supervisor at that time to develop a climate change research program. This was at the very start of formal climate change research in the United States. It was funded by the U.S. government and is still funded by the same program continuously today. And I was a little bit overawed, I'll have to say, by being at the University of Washington and being what was then the College of Forest Resources, because we had some pretty hotshot ecologists and scientists here. And it was a real honor to sit down the hall from these folks. And I was trying to figure out, what can I do that will make a contribution compared to what all these folks have done for their whole careers? And what I came to was that we had a wealth of knowledge, primarily on low elevation coniferous forest in the Pacific Northwest. We had the world experts on that. But for whatever reason, there was a pretty small presence in the scientific literature on the higher elevation forests. And I love hiking in high elevation forests, so this was kind of like throwing a rabbit in a briar patch for me. And so I thought, this is an area where I can make a contribution scientifically, and it's also an area that's probably going to be very important in terms of climate change. So these high elevation systems are very useful for looking at climate change for a number of reasons. You can see in this photo, there's quite a bit of variation across this small landscape, from heavily forested right up to tree line, the limit of where trees can grow. We see that the different topographic variation in this photo has a significant effect on where the trees grow. And if you look closely, you can also identify different tree species in this photo. In this photo, you can see where the trees are lining themselves up essentially across the old glacial moraines. So we have a nice legacy of past climates, past glaciers in this area that affect current vegetation distribution. We see the dense forests on the left side of the photo, which is north-facing. We have the more sparse photos on the east side. You see the alpine larch, the nice yellow color going straight up to tree line there. These trees in this photo, this is up in the Pasayten Wilderness on the east side of the North Cascades. The other thing that really appealed to me was, although these trees aren't as big as our kind of classic low elevation old growth, these are still old growth. Many of the trees in this photo, on average, are 300 to 400 years old, and we found quite a few larch in this area that were up to 800 and 900 years old. So just as old as some of our low elevation forests, maybe not quite as dramatic or charismatic, but just as old, just as functional within this environment, and they have a lot to tell us about past climates. If we go right up to tree line, we start to see these neat boundaries or ecotones. So you can actually see these things. And that's kind of nice for an ecologist. You don't have to necessarily take some complex measurements. You can just walk right to the edge, and you can see this border between trees and meadow vegetation. Sometimes the boundaries are very dramatic, like this little tree island. And I always get this feeling that there's very dynamic landscapes in these environments. I get the feeling that these trees are actually moving out into the meadows. It's the same feeling I get here, right at the very margin of tree life, where the trees are just barely surviving and they're only about this tall. And finally, there are places where you can see that very limit, as it's associated with snow, wind, and just plain being too cold for trees to grow. So for me, this was an incredible natural laboratory in which we could do both some groundbreaking scientific discovery as well as provide some insights on climate change into the future. So over the last 20 years, we have done a reasonable job, I think, of investigating a number of different topics. And I'm going to go over, just very briefly, where we have studied climate change effects in the Pacific Northwest. The dots I'm going to show on this map all represent different types of studies. And the main reason I'm showing you this is to make sure you know I'm not just pulling this out of my hat. And we've actually taken a pretty hard look at this topic over the last 2 decades. This dot indicates some paleoecological studies we conducted in North Cascades. The brown dots indicate studies of soil carbon and other soil factors. The cyan dots indicate tree regeneration studies that have focused primarily in the Olympics and the Mount Rainier region. The big yellow dots indicate large areas where we have collected vegetation data, vegetation distribution and abundance data. The orange dots indicate locations where we did studies on tree growth and climate. So we kind of zoom out here. You can see there's a lot more orange dots have appeared across this landscape. Not all at high elevation, many of them at low elevation. Across the Cascade Crest and from west to east from Washington to Montana. And then finally, the big red dots appropriately represent fire studies that we've done in the Northwest. So this is all the work of the graduate students and postdocs and folks that we've worked with in our lab here. And then today, we have expanded from the Northwest to the entire western U.S. in what we're called the Western Mountain Initiative in a collaboration with other scientists from USGS and various universities. And we're now trying to develop inferences about climate change at the subcontinental scale. So, this is a shot from Mount Rainier National Park. And again, these trees might not be all that dramatic compared to low elevation trees, but most of the big trees here are 400 to 500 years old. And we can see that the trees are basically moving out into the meadows, going down to the left. But even many of the little trees there are anywhere from 50 to 100 years old. But this is a very dynamic landscape. It's not at all static. We were particularly interested to understand how growth of these trees responded to climate over time. We do this in a fairly straightforward way. We core trees, as shown in the upper left there with these increment bores. We pull out little cores or cylinders of wood in the upper right. We measure them in the lab down there in the lower left-hand corner. And then we produce hundreds, if not thousands, of these little graphs, time series of tree growth over time. It's the data in that graph in the bottom right that we aggregate and analyze to try to pull out climate change signals of various types. So much of what I'm going to talk about in the next few minutes relates to this type of data. When we first started doing this work, we found pretty much the normal kinds of time series of tree growth from different locations, lots of up and down in these graphs, or what's called high frequency growth pattern. And that's fairly typical. Climate or weather varies from year to year, so you'd expect growth of trees to vary from year to year. But we also saw these lower frequency patterns where you could fit this kind of smooth curve there, this kind of undulating pattern, and thought, that's kind of interesting, and then went on. Because we could never come up with a good cause-effect explanation of that low-frequency variation in tree growth. So we figured it had to have something to do with climate. Now, at this point in time, early 90s, a lot more information was coming out about El Nino Southern Oscillation. I'm sure most of you are familiar with this. It's based on sea surface temperature in the equatorial Pacific and fluctuates on about a 3 to 7 year cycle, something like that. And we have extremes called El Ninos and La Ninas. This year we have an El Nino, which produces warm, dry weather in the Northwest. Last 2 years we had La Ninas, which produced all kinds of record snowfall and cold temperatures. That didn't explain the pattern. Then in 1997, there was a landmark paper published by my friend and colleague Nate Mantua and Steve Hare that documented how climate affected fisheries populations between the Pacific Northwest coast and southern Alaska. And they called the ocean atmospheric circulation pattern the Pacific Decadal Oscillation. This was a 20 to 30-year cycle over time, so kind of like El Nino on steroids, if you will. But when we started hearing about this, we thought this is kind of cool. And if you fit a smoothing curve through this one, that looks like about the same frequency as the one that we fit through that tree growth curve. And so the light bulbs went off. It's like we have found a connection here. Reason I mention this is not to say this is such a great discovery, but to give you kind of a preview of what I'm going to talk about later, namely the value of interdisciplinary communication and research. If it hadn't been for the Climate Impacts Group on campus, if it hadn't been for Nate Mantua, who was in fisheries and atmospheric science, we never could have made this connection. This was the first report of this type. And since then, people all over the West have documented similar patterns for a wide range of natural resource phenomena. So for tree growth in particular, this is a little bit of a messy graph. I'll try to walk you through this. We found that the patterns of growth lined up very nicely with the PDO, or Pacific Decadal Oscillation. The upper graph from the Northeast Cascades, a very high snowfall environment. The light gray line is the PDO index. And we show the warm and cool PDOs there from left to right. And we see that those curves correlate very nicely. During the cool PDO, we have high snowfall. That means trees have a shorter growing season, and that means they have lower growth, which is exactly what you see in the middle of that graph, and vice versa during the warm PDOs. Northeast Olympics, in this graph in the bottom, a dry environment, it's the same PDO graph, and we find that tree growth is inversely correlated. But in this case, it's because snowpack is high during the cool PDO, and the trees need that water, so they actually grow faster during those periods of time. Same tree species, similar locations, very different responses, but all correlated with these long-term climate patterns. Since then, we've learned that PDO affects all kinds of resources in the Pacific Northwest: fish, oysters, zooplankton, jellyfish, and especially snowpack, glaciers, and stream flow, which is a very important economic discovery, as well as our studies on tree growth and tree regeneration. So this was a tremendous linkage between atmospheric sciences, biological resources, water, all kinds of different disciplines. So one of the questions I get the most often is, okay, so you know all this stuff about trees, you've cored all these trees, what does that mean for the future? How are these trees going to grow in a warmer climate? And there are some different patterns we feel based on our data. First of all, if we look at the high elevation forests, most of them will probably experience a growth increase because of reduced snowpack. So it's not all bad news, it's not all gloom and doom. So the trees in this area, at least, will probably have increased growth. Mid-elevation forest, we're a little less certain, and it will probably depend on what the precipitation turns out to be in the future. Low elevation forests, we're very clear that most trees in low elevation forests will probably have decreased growth, and this is where most of our commercially valuable forests are. So just to hone in on species, our high elevation species like subalpine fir, mountain hemlock, lodgepole pine, all my favorites, a lot of those will increase in growth. Mid-elevation, kind of on the bubble, we're not sure, might not be much effect. Low elevation, some of our iconic species in the Northwest, such as Douglas fir, cedar, hemlock, and spruce, will almost certainly decrease in growth during the next century and beyond. We've also done quite a bit of work on tree regeneration or distribution and abundance of small trees over time. And regeneration is typically limited by things like snowpack, length of growing season, soil moisture in the summer. And with respect to climate change, what we are seeing is that regeneration at a lot of the high elevation sites is actually increasing. And it makes sense. Snowpack is reduced, they have a longer growing season, and they can grow faster, better, basically have a better chance of surviving. The exact opposite is true in the east side Cascades. Dry forests are going to get drier, so regeneration will probably decrease there. And just to give you a real-world example, this crew is up at Mount Rainier National Park in 1920, and some of you will recognize that as Paradise Meadows area on the south side of the park. And look at the background there. It's pretty much all meadow except for that one group of trees. And here's a photo from today. And the trees are moving in. What this doesn't show, that there was a big effort to cut trees in the 1960s. Thousands and thousands of trees were cut so they didn't take over the meadows in this area. Now, most people go up there to see the wildflowers, not to see trees. So the park managers will get an opportunity to make that decision again, whether they want to maintain the meadows or whether they're okay with the trees coming in. So we'll see how that pans out. But this is a very dynamic system. It turns out that this phenomenon is occurring throughout the Pacific Northwest and throughout western North America. So this seems to be kind of a universal phenomenon that may be related to increasing temperatures and decreasing snowpacks. Now, everything I've told you up till now may be of some interest, but it pales in importance compared to what I'm going to talk about next. And that is ecological disturbance, which will almost certainly change significantly as a result of a warmer climate. And the importance of this factor is that it will change ecosystem structure and function. So 2-3 degree change in temperature might affect growth a little bit up, a little bit down, but big fires kill all the trees on a particular landscape. Insect attacks may kill all the trees on a particular landscape. That's dynamic change. Some people talk about those as being ecological, breakpoints or bottlenecks or however you want to put it, but this is where the action will be in the future. Why does this matter? Well, extremes are typically the things that affect ecosystems the most. It's not the means. It's not that central tendency as shown in this probability curve here. So if we shift the distribution of temperatures, it has a much bigger effect at the extremes than near the mean. So if we were to take an event that currently might be, say, a 1 in 40 years you have a big flood, 1 in 40 years you have a big fire, and you shift that curve to the right, well, now it's going to happen once in every 6 years. That's the kind of thing that affects ecosystems. One of the things that we have not experienced very much since the early to mid 20th century has been drought. These are reconstructed droughts based on tree ring data that were done by one of my students. And what it shows is that prior to 1950, droughts were much more common in the Pacific Northwest. This is based on Columbia River stream flow. The 1930s peak there you see is kind of the famous Dust Bowl era. And then you look at the 1840s when there were 10 consecutive years of intensive drought. Okay, nowadays, if we have one year of drought, or 2 years of drought, people get pretty concerned about it. It becomes a big economic factor, it's a big policy issue, we have competition for water. What happens when that occurs for 10 consecutive years? We have allocated most of our resources, including water, based on stream flow and water supplies of the 20th century, the late 20th century, which apparently is not a typical period in time. What I'm showing here is more typical. So if this thing happens in the future, hold on to your seat. We're going to be in for a very interesting ride. A couple of years ago, I was asked to do a television documentary on climate change, and they're looking for short, pithy statements. You never want to go into too much detail for television viewers. And they said, if you can put it into one sentence, what will the future look like in this landscape? And I said, bugs and fire. They like that a lot. So that got me off the hook, although I don't like simplistic explanations like that. But I think there is some truth to it. The critter you see depicted here, not actual size, fortunately, is the mountain pine beetle, Dendroxenus ponderosi. And it is having a great time these days because of warmer temperatures. Warmer temperatures help to increase its reproductive rate, and it's expanding its range rapidly throughout western North America. The brown trees you see in the upper photo are mountain pine beetle mortality, and what you see below is what happens quite a few years after all the trees die and fall over. The reason it increases its reproductive activity is, first of all, the larvae aren't killed in the winter because it's warm enough for them. And second of all, it truncates their reproductive cycle from what's normally 2 years to 1 year. So those of you who are biologists and understand population biology and so forth know that has a tremendous effect on populations of these organisms. So they can reproduce quickly, disseminate themselves, and very quickly kill lots of trees. This is some data, a few years old now, mountain pine beetle mortality in Washington and Oregon. All the red areas indicate where trees are killed. You can see these are big landscapes, big landscapes. And those of you who have been on the east side of the Cascades in Washington, over in the Okanagan country, have probably seen a lot of these dead trees. If we look just at beetle mortality in eastern Washington, we see this graph here for ponderosa pine and lodgepole pine. And notice the shift that occurred there around 2000, 2002. The curve went up like crazy. Turns out this is happening at several locations in western North America right now. The poster child for mountain pine beetle is British Columbia, which has currently had about 25 million acres of lodgepole pine killed by pine beetle. Okay, so just for reference, Yellowstone National Park is about 2 million acres. So that's about 12 to 13 Yellowstone National Parks contiguously across the landscape. This graph shows a little bit of a cartoon on mountain pine beetle outbreaks in British Columbia, and you'll see red dots start to appear whenever there are outbreaks. So if you're patient, hang in there with me. We'll take this almost to the present, where it gets more exciting. Okay. That is ecological change, the likes of which we have never recorded in human history in western North America. Now, this is good or bad depending on what your values are. It's great for mountain pine beetles. It's great for woodpeckers. It's probably great for other types of organisms, but most people would consider this to be an adverse effect, maybe not irreversible, but at least it would take quite a while to regrow these forests in these areas, and it's questionable how this situation will be managed in British Columbia. Let's move now to wildfire. Now, of course, it's pretty logical that if the climate gets warmer, that we might expect to have more fires across the landscape. And this has been suggested as one theory as to why or how, whether or not climate affects fire or not. Some people think it's UFOs. This was actually published in this esteemed scientific document. And some of us thought, well, maybe there's something to this. And so we submitted a proposal to NSF, but they just didn't go for it. So we moved back to traditional science. I would not consider this to be interdisciplinary science, by the way. So just as a little bit of empirical data, scientists have to show graphs. We want to take a look at this phenomenon of wildfire across the U.S. over the last century or so. So some of my students have pulled together data on fire area burned across western U.S. Jeremy Littell, who was a PhD in our program, did an excellent job with some of this analysis. And what we found was that there was a lot of fire. This is acres burned on the y-axis. A lot of fire early in the 20th century, not so much in the mid-century, and lots of fire in the latter part of the century. This is just for federal lands in the big western states. And the way this is usually interpreted is that we started doing a really good job on putting fires out, and so we excluded fires, number of fires, area fire went down, and then we did such a good job at that the fuels accumulated, and now we're having big fires again. Has anybody ever heard that? Yeah. I asked that in a class just the other day. Everybody raised their hand and said yes. So that's what I call the fire dogma. And being rather skeptical about things, I decided to overlay this Pacific decadal oscillation pattern during the 20th century. And I know we have at least some pretty good statisticians in the house tonight. And so this is just a correlation, right? I think it's a pretty good correlation. I don't believe in coincidences very much. So it looks like, to me, that climate is having a pretty significant influence. And I cannot take credit for being the discoverer of this. I'll give that to my friend and colleague, Professor Jim Agee, who in his 1993 book on fire ecology first suggested that this pattern was due to climate and not due to human impacts. So we at least know that we have more fire now due to something, probably climate being the most important factor. If we zero in now on just the Pacific Northwest, national forests in Idaho, Oregon, Washington, and we line up the big fire years, years in which there are greater than 200,000 acres total since 1916, and we array those by which ones occurred during cool PDOs and which were in warm PDOs, about 3/4 of them occur during the warm phase PDO. So, okay, when it's warmer, you get bigger fires. That's kind of makes sense. But the nice thing about this is it gives us some predictability. So if we know we're in a warm PDO, we can expect more fires. We can also maybe suggest that if the future climate looks more like a warm PDO, if we get into a warm PDO forever, then we can expect more fire forever. At least that's a possible future. In some empirical analysis of that same data set done by my colleague Don McKenzie, he suggests that with a 2-degree increase, annual area burned will be 2 to 3 times higher in the western U.S. Okay, so that doesn't mean too much, but I want to put this in very, very practical terms. The agency I work for, U.S. Forest Service, currently spends about 50% of its total budget on fire management and fire suppression. So if we double the amount of area burned, so that's 2 times 50, very close to 100% of our budget potentially could be spent on fire. So that has some pretty serious policy implications. When you start talking economics, you start basically taking an agency and potentially allocating more of their resources to one particular resource. That's a concern. Warming also interacts with a wide range of factors in natural environments. I just want to show you one example of what Don McKenzie and I like to call stress complexes. This is the interaction of different stresses on forest ecosystems. We have here is a kind of a little box and arrow chart for a lodgepole pine forest system, which is shown in the lower left there. And I'm just going to walk you through here on the temperature effects, higher temperatures, more severe and extended droughts, increased bark beetles. So now we're putting both of these things together. And you have the possibility of increased fuel accumulations, larger, more severe fires, and perhaps some change in species ultimately. So I just put this up here to demonstrate that we could well have these interactions and synergies of different factors that could have greater than additive effects on forest ecosystems. And we are, in fact, observing some pretty big fires, especially during the last decade. Some of you are probably familiar with the tripod fire on the Okanagan-Wenatchee National Forest, 175,000 acres. Much of this fire burned through bark beetle mortality, so that was part of the fuel load. We have other major fires during the last 10 years. The Biscuit Fire in southwest Oregon, 500,000 acres. I could make a long list of these fires in the Pacific Northwest. I am not standing here to tell you that these are caused by climate change. What I am saying is that if we have a persistently warmer climate in the future, we could have more larger fires. So one of the things I like to challenge myself with, and one thing that I'm charged to work with the Forest Service, is how do we manage for resilient systems in a warmer climate? This is one kind of solution that's been suggested, is that particularly for our east side Cascade forests, where we have these dense forests, not particularly high vigor, trees are growing slower, that we do some thinning in those forests, we remove the surface fuels, and we create a more open environment that may have been more like what it was prior to about 1900, when fires ran through these forests every few years. Some people might say that lower image is not very desirable, that's unappealing. The upper image is actually much better for songbird nesting habitat, for example. So if you were just managing for songbirds, you wouldn't want that bottom graph. So there's always trade-offs in any of these choices that we make. It's not that simple. There is some evidence that this kind of management can increase resilience. Susan Pritchard, who got her PhD in our lab several years ago, has been doing some studies on the tripod fire, and she compared areas that did and did not have treatment prior to the fire from thinning and prescribed burning. The upper figure shows a forest that did not have any treatment and pretty much got cooked. The lower figure shows a forest that had thinning and prescribed burning, pre-fire, and it had very low tree mortality. And I didn't cherry pick these data. This is very typical of what we find in that landscape. Another slide from the tripod fire. This is some work that was done, just completed recently by Christina Lyons-Tinsley, master's student in our program. This is a little bit higher elevation, and we notice that there are all these green patches out there. What were the green patches? The green patches were all areas that were clear-cut 20 to 30 years ago. They were and also had the surface fuels removed. They were the only areas in these enormous landscapes that had little or no mortality from the fire. All the older forests pretty much got cooked, as you can see. So could we use timber harvest, at least selectively, as a tool for building resilience? And I know that that gets into policy issues and philosophical issues and so forth, but these are some things we're starting to observe in these large fires. Bottom line is we have to manage across large landscapes. We can't take it 100 acres at a time. We have to take it more like 1,000,000 acres at a time to really make any difference. And we may want to have some variety out there so that no matter what the future looks like, some portions of these landscapes will continue to function into the future. One thing I've worked on quite hard over the last 3 years is trying to figure out how we can actually prepare for these various futures. Now, whether or not we actually go whole hog on mitigation and reducing carbon emissions, climate is going to continue to warm for the next 100 to 200 years. Even if we stopped emissions today, that will continue. So, in my mind, we have to prepare, regardless of how warm it gets. So I'd like to suggest 8 things that could be done to create more resilient ecosystems in the future. One is to increase landscape diversity. Do this at large scales, try different treatments, use different spatial configurations, do some experiments at large scales, and we need to do things in bigger patches, not smaller patches, while keeping everything connected. Maintain biological diversity. This is kind of the motherhood and apple pie adaptation strategy. I mean, who isn't for maintaining biological diversity? But there's some very good reasons for that. We need to keep as much genetic variability in the environment as possible so some of those genotypes will survive into the future. And we also need to identify those entities that are potentially sensitive to increased disturbance. Future fires and insect attacks is not an if question, it's a when question. So we may as well prepare for them. And what do we do after we have those insect attacks and after the fires? My idea is that you treat these as normal periodic occurrences. And so when you have that big fire, you can go out on that landscape the next day and you know what you're going to do in terms of managing that landscape. Strategy 4 is early detection, rapid response. This basically refers to things like exotic species. If you know you have a new exotic species out there, some kind of weed, jump on it. Get rid of it. Whenever you have a new factor that you think could be deleterious, deal with it through active management. Don't, wring your hands for 10 years and do 42 environmental impact statements, by which time it gets away from you. Just my opinion. We also need to be realistic about what we can actually do in the future. Now, we don't know these climate thresholds for too many species. But where we do, let's identify those and make realistic decisions. One thing we know quite a bit about is Pacific salmon. And Nate Mantua, who I mentioned earlier, has a very nice paper coming out fairly soon in the journal Climatic Change that documents the expected decrease of suitable salmon habitat in the Pacific Northwest. And it's not a happy thing, I'm afraid to say. But if we know that there is a stream where the water temperature will almost certainly become too high to support salmon, how much money and effort should we exert trying to protect salmon in that stream? Let's spend our money where we have a good bet and not bet on the long shots. Restoration of ecosystems has become a big paradigm in the Pacific Northwest and elsewhere. We need to include climate change as part of our restoration efforts. We need to reduce emphasis on historical perspectives. There's this idea, well, we want to return it to the way it was in the 1800s. We want to return it to the time when European settlers came to this country. You know what? We'll never be in that climate or that situation again. What we need to do is prepare for future climate scenarios. And so This will take a lot of creativity. It'll be some educated guesswork, but we have to move forward and not keep referencing historical perspectives. This adaptation strategy is really more of it's one that we need to have our leaders take care of for us and address regulatory issues, policy issues, and so forth. Sometimes regulations are your friend, and sometimes they're not your friend. And we all know in this room the Endangered Species Act has pretty much ruled the roost in the Pacific Northwest in terms of guiding resource management and decision-making over the last 2 decades. Some of these regulations get in our way of doing active management to create resilient landscapes, and if there's a high emphasis on protecting a particular salmon stock in a stream that's going to get too warm to support that salmon, we have a really interesting social and biological conflict there. So these are pretty sticky issues. I'm not going to go into detail, but unless we address these up front, we're going to find there's a lot of barriers to being able to adapt to climate change. The last one I'm going to throw in is there's going to be some surprises, so let's get ready for them. Let's think big. Let's think about the big droughts, the big fires, species extirpations, and so forth. And if those happen, what do we do about it? How do we prepare for it? Okay? So when they happen, let's not have them be catastrophes. Let's have a plan in place to deal with it, much like Noah did there with his boat. Now, before I move on, I want to tell you one thing about these 8 strategies. I didn't develop these. These were all developed by National Forest resource managers, who are the ones who should be developing adaptation strategies. They understand these landscapes, they're familiar with them, they manage them, and the way we go about this adaptation business between scientists and managers is the scientists provide the scenarios, ask the questions, the managers provide us with the answers. They like it, we like it, and it makes sense that we have that kind of a partnership. So I suggest this is a very good way to move forward. And the last thing we want to get, the last situation we want to get into is having scientists basically dictating to resource managers about what they should do. That is not our job. We are information providers to resource managers and decision makers. So I'm going to, with your permission, we'll turn the lights up. But at this point, you know, you might be thinking that that light there is either a train coming right at you, or it might be a light at the end of the tunnel. So I'd like to pursue that line of discussion just a little bit with my remaining remarks. Well, April 22nd, next month, is the 40th anniversary of Earth Day. And I remember that first Earth Day pretty well. I helped to organize an event at my high school in the south side of Chicago. We put a tremendous amount of effort into planning this really cool program for the students in the local community. And I went to a high school that had 5,000 students in it. And we had a crowd of about 60 people that night. So it was sort of an inauspicious introduction to the world of environmental science, but I don't know if that inspired me or not, but I persisted, and that was the last event we planned. But I figured I had to do something about it, and I know a lot of people in this room are Earth Day babies themselves, and that's why they went into natural resource science. So we've had this 40-year period where there's been arguably a big focus on environmental issues in the United States. And we've had 40 years of science. I just looked this up on the internet today. The Ecological Society of America has 10,000 members. The American Geophysical Union has 58,000 members. Every year there's thousands and thousands of scientific articles published. We all go to meetings, give talks and papers. The National Science Foundation budget is $7 billion a year, a good chunk of which goes into environmental research. So why don't we have more solutions to our problems? What are the taxpayers really paying for when they give me my salary and they send me off for 30 years to do natural resources research? And why don't we have more answers? And I'd like to pursue that just a little bit, not in a pejorative sense, but really in a sincere quest to find perhaps some pathways through this. Now, if we look at scientific research in natural resources sciences as a whole, the vast majority of it focuses on what I call knowledge discovery. new facts, new species, new processes, new structures, new things about certain things. Okay, so that's what I call knowledge discovery. But science can also consist of synthesis of existing information. It can also consist of taking that existing information and applying it to real-world problems. And I think somehow that ratio is really skewed right now, and perhaps to our disadvantage in terms of solving some of these environmental issues. The potential application of information is a very critical research context. I dare say, I am guilty of this, just like other folks are, that you start doing research on something because you think it's fun, because you think it's interesting, engaging, and because you have some funding to do it. But are you asking the right questions due to those motivations? Or should your motivation come from talking to a national forest manager, or a water resource manager, or someone who is simply managing a natural resources division for a municipality? The key here is to talk to these folks before you do the study and to include them throughout the study so that when you come out the end of the pipe, the results are relevant to what that person needs. Now, I review a lot of proposals, a lot of research proposals from NSF and different organizations, and very rarely do those proposals contain a plan for science delivery or technical transfer of scientific information. And most of us publish our results in scientific journals because that's where we get our rewards, that's how we get our pay increases, so forth. That's where we get the glory, if you will. But you know what? Resource managers in the national forests and national parks don't read journals. They really don't. And you could publish the best article in the world, they probably aren't going to read it. So often in proposals I see, well, we will produce this website and we will post our results and our papers on this website, and everybody in the world then has access to it. And that's what I call the if you build it, they will come concept. And again, it's not very effective. You can't just hang out your shingle and expect people to find it. So we need, as scientists, we need to be proactive about getting our results out to people who can use it quickly and effectively. We cannot afford to go through another 20, 30 years of hobby research. I really do believe that interdisciplinary research is the way that we should move forward. In the future, I've tried to give you some examples of this in my talk today. There are relatively few successful examples of interdisciplinary research in the United States. There's a lot of multidisciplinary research. I would say that a lot of the research that occurred during the days of Northwest Forest Plan development, excellent research, but it was multidisciplinary, not interdisciplinary. And when I use this term interdisciplinary, I mean both within and across biological disciplines and across physical, biological, and social disciplines. So what we need for the future, for dealing with climate change, we need ecologists who understand geology and soils, and we need geologists who understand forestry. We need wildlife biologists who understand policy and risk management, and we need policy analysts who understand conservation ecology. We need these people who are cross-trained, not just familiar with these topics, but actually understand them. And we also need to work together to establish priorities for research. Right now we have this kind of random roller coaster of how people derive priorities for research without a lot of strategic approach to it. Now there's a reason why we have this, and that's primarily that organizational cultures, traditions, and structures typically don't reward interdisciplinary research. We reward individual accomplishment, fat curriculum vitae, and, if you will, big impact science in terms of how it contributes to scientific discovery, not necessarily to applications. But we do have some great examples of interdisciplinary on the local scene. I'd like to again cite the Climate Impacts Group, which is part of the College of Environment. Professor Ed Miles, who is director, has done an excellent job of pulling scientists from across campus, from federal organizations and universities, is a group who truly talk to one another and have made significant discoveries and applications of their scientific discoveries across the Pacific Northwest. I think that's a great, great model to emulate both at the University of Washington and other locations. One of the most exciting things about the formation of the College of Environment, everybody saw these cool posters, banners that were in the reception room this evening. One of the really attractive things about this college is that we now have this opportunity to put interdisciplinary research on the ground and we can institutionalize that. And if we do that, I think we'll make some really big impacts in the Pacific Northwest and beyond. If we focus on those issues that have the highest relevance for environmental issues, decision-making, and policy, that will have a big impact on future generations. The last thing I'd like to mention is the concept of partnerships between scientists and between the users of information or resource managers. Scientists need to talk to the users of their information. Users of the information need to talk to scientists. I always call it, take a resource manager out for lunch, or take a scientist out for a beer. You never know what you're going to come up with in this casual setting. It's based on personal relationships, but if we don't talk at all, we'll never make those connections. In real estate world, they talk about location, location, location. And for this partnership concept, it's communication, communication, communication. Now, sometimes that's not easy because somebody told me once that people in the general public don't always understand what scientists say. Can you imagine that? It's hard to believe, but I guess it's true. So everybody needs to make an effort. If you feel like you're going this way, scientists might need to come down a little bit, resource managers might need to come up a little bit so you make a good connection. It has to be a true partnership. I think there's a tendency, in all honesty, for some folks to view federal agencies as funding sources, if you will. Give me the funding, give me 3 years, I'll get back to you. That is not a route for effective or collegial science that's going to be relevant. So we need to talk all the way through the process. And finally, we need to work with those clients at various levels, not just the higher end folks, but also the folks out in the field. We need to work with them on final delivery of the products and information from that research, and we need to create ownership on their part of that scientific information, and that will provide great payoffs into the future in terms of additional collaborations as other issues arise. I'd like to close tonight by offering a challenge to everyone in the audience, to the College of the Environment, and to myself to continue to pursue this line of interdisciplinary research and partnerships into the future. I really think it will pay off in great benefits. It will result in more effective research. It will result in more timely applications of research. The actions that we take in the next 10 or 20 years will make all the differences to whether future generations view us as heroes or as villains. And I don't know about you, but I'd much rather that my great-great-grandchildren would have my picture proudly hanging on their wall than to have it hidden in the attic upstairs because of what we did in the next 2 decades. Thank you.